SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. Last time what we said, we started discussing about sprays and droplet breakup models. So, in this particular presentation we are going to show that we already covered a little bit of this. We said that usually it is a complex process. There is usually a liquid sheet which is very much like that you see over there. This liquid sheet subsequently breaks up, okay, and forms ligaments. So, it's ligament like structures you can see there, right. These would be kind of ligamentish kind of structures, right. There will be also ligament structures there if you zoom in, right. So, these ligaments first form, and then these ligaments, what happens is that these ligaments then further undergoes further breakup and forms smaller droplets, okay. So, smaller droplets will be like that, those kind of droplets that you see, right, these. Now, these droplets, depending on the load, that means depending on the aerodynamic breakup, aerodynamic forces, or the force, or whatever forces that you are applying, this can undergo further breakup into even smaller droplets, okay. So, usually the spray zone is divided into a primary atomization zone, which is very close to a nozzle where the liquid sheet breaks up into ligaments and things like that. Then there is a secondary atomization zone which is further downstream of the nozzle, right, where we actually get these smaller droplets undergoing further breakup, okay. So, that is the I mean that those are the processes. Now, in between these droplets starts to interact with the flow has an effect on the droplet dispersion, how the droplets are actually spread, how much the droplets actually evaporate also. So, all those things starts to happen, okay, when you actually have a spray injected into a high velocity fluid, high velocity gas phase flow field usually. Now, events like evaporation and mixing happens a little later, okay, that is in this zone it starts to happen. It does not really happen there because this process is very fast. It starts to happen in this zone, starts to become important in this zone, because evaporation, as we already learned, is a very slow process, right, and these processes are very fast. They can be microseconds and that order, right. The breakup process can be very, very fast itself, okay. So, so these nice pictures actually shows that how the droplets actually break up, and they are not spherical. That is what we told, that they are like this or they are like that, all kinds of shapes, okay. Obviously, all these shapes are unstable, right, because as you know the droplet or liquid blob always tries to be spherical no matter what, right. So, in that process it starts to split, okay, it generates these smaller and smaller droplets. As it becomes very small, surface tension starts to become very, very important, and those droplets becomes very stable, okay. So, when evaporation and mixing takes place, the droplets can be considered spherical. So, the analysis, all those analysis that we did earlier on droplet evaporation holds, but not for very large droplets, right, because large droplets are unstable inherently, okay, especially in a high speed flow. It depends on the flow conditions. It is not like that they are unstable by nature, okay. It is like it depends on the flow, okay. So, let us look at the governing parameter, since you see the all the spray problems actually involves interfacial tension, right. So, that should be the main governing parameter. So, sigma, which is the surface tension, has to come in some way, right. So, let us look when you actually have a droplet or an interface, okay. There are two types of forces that usually acts on an interface, right. So, if this is a droplet, let us take the example of a droplet. There is a very high velocity fluid, gas phase flow field that is coming and hitting the droplet. So, what will happen is that this will give rise to a force around the droplet, right. So, that force is nothing but the aerodynamic drag. Now, aerodynamic drag is given by CD. CD is the drag coefficient. This is the diameter of the droplet, this is the gas phase density, and this is the relative velocity between the droplet and the gas phase, right. So, this is the relative velocity. So, the droplet may be also moving, the gas is also moving, right. So, it is the relative velocity between the two that actually determines the what is the drag force. So, as you can see, if say for example, we have this duct in which there is a very high speed flow. So, this u is of the order of 100 meter per second, it can be much higher than this, okay, and the droplets are say injected at say 5 meter per second, right. So, this is a droplet which all of a sudden sees a 100 minus 5 something like a 95 meter per second flow field, right. If I am a droplet, all of a sudden I see that I am hit by a 95 meter per second, and 95 meter per second is very high, okay, velocity stream. Okay. So, it is almost like you are in your home, you suddenly go out on the sand, there is a hurricane going on and you suddenly feel that there is a blast of wind that is hitting you, right. Now, that is nothing but the aerodynamic force that the droplet experiences as it gets exposed to a high velocity fluid flow, right. So, as you can see, larger the value of this is square, remember. So, if larger the value of this, more is the aerodynamic force, simple, right. So, if you inject, if this flow velocity instead of 100, now it becomes like say 300 meter per second, okay, sonic condition, or if it goes to say 500 meter per second, hypersonics or supersonic conditions, okay, what you will have, this droplet now will feel 500 minus 5 square, okay, that will be the value of this guy, right. So, that is an abnormal flow velocity. Now, what is the restoring force? That is, so this force tries to deform the droplet. So, if you are a droplet, you will now start to be deformed in that particular fashion, right. You will no longer remain spherical, okay. But the droplet has got an ally, its ally is basically its surface tension, right. Surface tension always tries to restore, you want to stretch it, it tries to restore you back, right. So, what will be the surface tension force? That is given by sigma into the perimeter of the droplet, right. So, that is the surface tension force, that, because remember surface tension is per Newton per meter, right. So, that is the surface tension force that is essentially restoring in nature. That means, the air tries to, or the aerodynamics tries to deform the droplet, surface tension tries to restore it back into this particular shape, into this spherical shape. As we know, spherical shape is the most stable shape, we already did that. Okay. Now, in the limiting case, when both these forces are the same, right, okay, you can equate the two, that is the drag force is equal to the surface tension force. So, basically you equate the two and you can get an expression like this, right. Now, this expression, if you look on the left hand side of the expression and the right hand side, both are non-dimensional in nature, right. Okay. So, if you look at the left hand side of this particular expression, you will find that it is a quantity, it is a peculiar quantity, right. It is a peculiar quantity which is basically given as rho of the gas phase, then this is the relative velocity square, right, divided by the surface tension. So, this quantity actually implies that this is a ratio of the inertial force is basically the aerodynamic force divided by the surface tension force, that is exactly what it is, because you have equated these two, right. So, divide one by the other basically gives you the inertial force divided by surface tension force, right. So, this particular quantity has got a name, it is called the Weber number, or we write it as WE, right. So, what is the Weber number actually designate? So, if the Weber number value is very high, okay, say it is much greater than 1, what does that imply? That implies that your inertial forces, that means the aerodynamic forces, are much more than your surface tension forces, right. Okay. So, that means your Fd is basically much greater than your F sigma, right. As a result, the droplet will distort, it will no longer remain spherical. Whereas, if your Weber number is much less than 1 or less than 1, let us not say much less than 1, let us say that it is less than 1. Okay. In that particular case, you imply that your surface tension force, okay, is actually winning over the aerodynamic force. This can happen when you are injecting the droplet say into a very low speed say cross flow. Okay. In that particular case, okay, we imply that the droplet will not be deformed, okay, the deformation of the droplet will not take place. So, this quantity Weber number basically becomes a very interesting parameter. It says when Weber number is greater than 1, disturbance amplifies, basically leading to breakup of the droplet, or in other cases if this says this is a jet. So, we have done it for a droplet, it could be also a jet, right, which is moving at a velocity, there is a difference in velocity between the two. So, there will be shear at this created at this interface, right, okay, and that will also lead to breakup in a very similar way. So, there also you can define Weber number. Okay. If Weber number is less than equal to 1, surface tension dominates and results in the damping of the disturbance. That means the droplet will not break up or the jet will not break up. So, Weber number becomes a very important parameter. It is basically the ratio of the inertial force by the surface tension force. Like Reynolds number was inertial by viscous, Weber number is inertial by surface tension, because these are the two quantities that are relevant in the current situation, right. Okay. So, that is an interesting observation. So, as you can see, so the Weber number can come here in this kind of a situation, or it can come in the case of a droplet. So, you take one of these droplet out and you can see what is the flow field around it, right. Okay. So, what is the role of viscosity? Now, we have said that it is inertial by surface tension, right, essentially, right. We have not said anything about the viscous force at all. Now, you know that the breakup process is not an instantaneous process, right. So, you have a droplet which is facing this gas phase flow field, right, that is what we covered. This first deforms, right, the droplet will first deform, it will deform more and then it will break up, right. So, it will be several stages, maybe next step will be like this, after that it will be like this, then after that a small droplet may come out from both sides, right. There is a process, right. It is not like that this immediately breaks up, okay. There is a finite time that is required, it may be short time, very short time, but that time is actually required. So, if you look at this cartoon over here, this will also tell you the same story, that there is stretching, lot of stretching that happens, right. Then there is end, from the end points the droplet starts to basically be ejected, right. So, my point of view over here is very simple, that there is, for this kind of secondary atomization process, because it deals with a droplet, right, there is a finite time that is required, and that invariably involves some kind of a shape deformation, right. Now, whenever there is a deformation of shape, okay, see both the viscosity as well as the surface tension tries to restore it back, okay, viscosity tries to damp out that effect, okay, tries to damp out that effect, okay. So, when we compare, say for example, the viscous and the surface tension role, okay, we get something like a capillary number. It is called a capillary number, once again a non-dimensional number, okay. It is a ratio of basically nothing but the viscous force to the surface tension, right, okay. So, if the capillary number is very low, right, if the capillary number for porous media and other things, okay, the capillary number becomes very important, okay. It also becomes important, you have to know the relative dominance between viscous and surface tension forces, right, okay. So, capillary number much greater than 1 and much less than 1, this kind of scenarios can happen, right. Normally they are very small numbers to begin with, okay. But if you want to not this is between the family essentially, right, it between viscosity and surface tension, what they are actually doing to restore the droplet back. But balance between viscous, surface tension and aerodynamic force, all three combined, is given by a number called the Onsorge number. Onsorge number includes the effect of surface tension, viscosity as well as the aerodynamic force, okay. So, this is the number, and this is one of the most important number that you will ever get, right. So, Onsorge number determines whether viscous dissipation or viscous effect on the breakup process is dominant or not. In many of the cases you will find it is not, but okay, in some cases there will be a lot of role this Onsorge number will actually play, okay. Now, this is for a uniform flow field, the Weber number. The Weber number is very difficult to define when you actually have a fluctuating flow field or you have a flow field which is more complicated. So, there can be variations of Weber number. For example, when acoustics is important, you can define something like a Weber number acoustics. Okay. You can define something like a Weber number based on circulation. Okay. You can define a Weber number based on some other parameters, whatever is it can be. If there are other types of forces that are present, okay, you can define a Weber number based on that. I will call that Weber number x, right. So, Weber number in itself, okay, just means a quantity which says what is the relative importance of whatever the force that you are dealing with, whether it is aerodynamic, vorticity driven, whatever it is, right, compared to the surface tension. So, the lower part, that is the denominator, always remains surface tension. Okay. It is a force which actually changes, right. So, do not think that Weber number is just this. This is the most common definition of Weber number, okay, but there can be other definitions also, right. Okay. So, Onsorge number and Weber number are the two main parameters that you will ever be concerned with in the course of this particular study and beyond. Right, yeah, sorry. So, in the Weber number, I am sorry. So, here of course, there is a D which was missing, right, because this one of the D cancels, the other D actually remains. Okay. So, the Weber number comes here with a D. Okay. So, there is that is the length scale. I am sorry about that. So, the Weber number here is a D, that is the definition of Weber number. Okay. So, that makes it non-dimensional. D is basically the whatever is the length scale, here is the length scale of the droplet. Okay. So, that is the Weber number definition, but anyway it is a non-dimensional number, that is the Onsorge number, this is the Weber number. Okay. Now, the influence of Weber number on secondary atomization has been a well studied problem, okay, and there has been some phenomenally great work that has been done. One of the great papers has been by Jerry Faith, okay, and there he actually showed that if you plot the Weber number versus the Onsorge number, remember, look at the values. Onsorge number is usually starts very low and goes very high, that viscous effects when it becomes very important. Okay. You see that there are several zones, and this is the density ratio has been maintained between 580 to 1200. Okay. So, 1000 will be like for water. There are fluids which can go a little below and a little higher, right. So, that is the density ratios that we are dealing with, and they have done it for all kinds of liquids like N-heptane, water, glycerol, as you know, is very viscous fluid, okay, very viscous. Okay. Then there are all other kinds of fluids that has been attempted. Okay. Glycerol 92% makes the fluid very viscous basically. Okay. Now, if you look at this particular problem now, this Weber number versus Onsorge number space, okay, there are several regimes that are available in this particular space. Say for example, when you actually have a very low Onsorge number, okay, you say in this zone, let me draw a line through it like that, right. Okay. What you go is that you go from this domain, which is like deformation is very small, that means the droplet deformation is very small, progressively goes higher because you know that the Weber number is increasing, right. So, naturally it will go high. Then there is oscillatory deformation, that means the droplet will start to oscillate and show shape deformations. Then we will see some varieties of breakup things like bag, multimode and shear. So, this is across this line, right. As you progressively go to a little bit higher Onsorge number, you basically get the same thing, because you see that this space is not changing that much, right. Across the board you see the same thing, right. So, for 2 orders higher Onsorge number, you do not see a difference in the breakup mode, right, for the same Weber number. If I just cross the same Weber number and that is very high, this is not very high, it is about 50, okay, you see that you still fall within that multimode kind of a breakup, right. But however, this curve starts to move upward if you look at the slope as you go to very high Onsorge number, right. So, that means now if I go to this particular line, what do you see over here? If I now take the same Weber number, okay, you will find that the deformation will fall somewhere here, right. That means there is a smaller amount of deformation, because this is that less than 20% deformation line, right. Okay. So, you can see that progressively it becomes harder to break the droplet. Say if a droplet is undergoing multimode breakup, right, it is very difficult to achieve multimode breakup, okay, when the viscosity is very high, when the Onsorge number is very high. Got it? Clear? So, Onsorge number, as you can see, rightly scales with the mu L, right. Okay, there is a Weber number component over here as well, okay. But what it generally implies is that this zone, as you can see, this gets expanded, right. So, for the same Weber number, where you are getting like less than greater than 10% deformation, now you are getting less than 5% deformation, understood. So, it becomes progressively harder to basically atomize the same thing, okay, in a particular mode. So, these curves, but the interesting part is that up to a certain regime, up to here, say for example, right, which is very close to something like 0.5, okay, it does not matter whatever is the Onsorge number value, it still shows breakup in the same way, okay, because these lines are absolutely flat, right. Of course, there is some oscillatory response curve which actually varies a little bit, but you can see that there is a zone, big zone, where this Onsorge number does not seem to have much of an influence, but it starts to have a lot of influence in the later part from the upward swing of the curve that you see over there, okay. Okay. Now, we have said that there are different modes of breakup like multimode, oscillatory, this and that, okay. So, one of the modes that we are going to look at is the vibrational or the oscillatory mode of breakup. This happens for a Weber number range of about 10 to actually 11, okay. So, 10 to 11, it basically falls in this particular range, so to say, right. So, in that particular range, what happens is that the droplet undergoes this almost single mode of breakup. You know what a single mode of breakup is? I mean, the droplet can show this kind of modes also, right. Single mode is like that, it is like across 1 degree of freedom. So, it is basically oscillating in a particular direction. It is like a 1 degree of freedom spring mass system. So, it is basically being stretched, and so it just basically goes that way and then it comes back to form the spherical shape, right. So, this mode of breakup is basically called vibrational breakup, and we are going to see when we do the tab model that what this vibrational mode of breakup is. There is something called a bag breakup, that means you can see that the droplet becomes like a pouch, right, and then it basically inflates like a spout, like a pouch, okay, like a balloon, right, and then it kind of atomizes from this rim, and you get all these smaller droplet sizes. This happens at a progressively higher Weber number, okay. Then this multimode breakup that you see over there is this, okay. So, you have a protrusion coming out, is similar like a bag, then you have a protrusion and then it breaks up into the smaller droplets, okay. Then shear thinning type of a breakup, shear thinning breakup means from the side of the sheet, okay, from the deformed sheet, okay, this is like a sheet, okay, it is like a sheet. If you stretch a balloon, it is like that, like the stretched balloon, and from this edge you start having this multiple droplets being ejected, okay. So, that is like a shear thinning type of a breakup, happens for very large values of Weber number. Then catastrophic atomization happens when there is like no random order, is a randomized kind of a process. The breakup is so violent, right, that it basically breaks up, there is no fixed pattern in that, like this has got a particular sequence of events. First it inflates, then there is this protruding ligament, and then it breaks up, okay. Here it first thins along the sides and then the side starts to atomize. So, there is a process, there is a certain time sequence history, right. This actually atomizes like it all of a sudden, it is like violent atomization, happens for very high Weber number values over there, right. Very high Weber number values is corresponds to actually this kind of regions, right, over there, like above 350. Okay, so, this is about 100, that is about 1000. So, 350 will be anywhere up this line, okay. But once again, viscous, if you have a lot of viscosity in your system, right, that mode may be very hard to achieve, right. You try to atomize honey, honey is highly viscous, right, try to atomize it and see what happens, okay. So, just to finish, before we finish this particular part of the lecture, we see that vibrational mode of breakup happens like this. So, there is a nice spherical droplet, it just deforms like this, it is a single mode, and then you generate two daughters, and this might undergo this cascade once again, okay. So, this might undergo the same thing and break up into two more, right. This can continue, okay, till you get the Weber number actually less than about 5 or 6. Okay. Once you get that in that range, then this droplets becomes very stable, right. Then the back type of breakup, you can see that this is the back growth. So, initially it becomes like a disc. Okay. So, at the center of the disc there is a lot of pressure, right. So, if you have a disc, right, it is like a liquid disc, remember, and at the center if there is a lot of pressure, then this liquid disc actually inflates like a balloon. Okay. So, this is the balloon made of water or whatever fluid that you are concerned with. Okay. This sheet actually gets stretched and stretched and stretched and stretched till it becomes very thin at the top, right, and then it bursts. It is like a balloon bursting. If you inflate it too much, if you try inflating a balloon and pump in lot of air, what will happen at the end? The balloon will just burst, right. So, you get this very fine droplets that are coming out of this. Okay. And the time scale of this breakup is given, but we will come to that what that actually means. Okay. You will not have any idea that what those means exactly. Okay. This is also very similar, but there is that protrusion, that is that protrusion of the ligament, right, that actually creates this kind of small sheets, this kind of small droplets. Okay. As we already talked about shear stripping, we saw that this also becomes like a flat disc kind of a thing with true protruding ligaments, which is very, so these are very very sharp. Okay. So, from these points the droplet starts to come out. Okay. So, there are mechanisms and this continues, you can see this is like a cascade, this continues. Okay. Okay. So, catastrophic, as you can see, the catastrophic is like that, there can be lot of events like this. There are something like wave crest stripping which is very much similar to this, okay, but it does not happen exactly in that way, but you do have a disc which basically perforates, which basically strips from the sides. Okay. So, that is also can happen. All this happens because the flow creates a lot of instabilities along the surface. Okay. So, these are the different breakup, these are broad phenomenology of breakup, and then you see all these breakup times are also given there. So, in the next class what we are going to do, we are going to look at the first of the models, okay, and see that what that actually does. Okay. Thank you.